Okay, so we are entering the solutions and solubility unit, and one of the most common or universal solvents for polar substances is water. So we're going to talk a little bit about the unique properties of water. So water is actually so unique, you could take entire courses on the chemistry of water, but we're just really going to scratch the surface here. So the first two lessons are a little bit of theory in them, and then we'll move more into the quantitative side of it. Okay, so water is H2O, and if you remember from the first unit, this is its Lewis structure. Its molecular weight is 18 grams per mole. Oxygen's polarity is, its electronegativity is 3.44, and hydrogen's is 2.2. So when you subtract them, you get 1.24, which is polar. So what happens is that means that the hydrogen's end is slightly positive, and oxygen's end is slightly negative. And so then the water molecules can be attracted to each other, which is very, very vital to really life on Earth. So what happens is you get this sort of matrix of water molecules. So if you remember again from the first unit, these dotted lines represent hydrogen bonds, which are the intermolecular force found between water molecules. And so really you could draw here, there would be, like if there was another one over here, you could draw some more in like here. So you get this network of water molecules, and the space between the water molecules, the space here, is actually bigger when it freezes, which is not a common property of frozen substances, which makes life possible really in the wintertime in aquatic systems. So when most of the unique properties of water are due to the hydrogen bonds and the polarity between the water molecules. So when you have a compound with a similar molecular weight, one of the best examples is methane, which is 16. And we just said that water was 18, so that's pretty close. Methane, which is natural gas, is a gas at room temperature, whereas water is a liquid. So the hydrogen bonds are very strong, keeping the water molecules closer together. And the stronger the bond, the more energy it takes to get it apart, which leads into water having a high melting point and boiling point. Oh, so that point right here. The stronger the intermolecular force, the more energy needed to get molecules apart. So because water has strong hydrogen bonds between molecules, it takes a lot of energy to get them apart. And this, I think we did talk about this. You just assume that boiling is a hot thing, like changing from a liquid to a gas, because we're so used to water boiling at 100 degrees Celsius. It's painful to touch. Whereas there are some molecules like methane that change into a gas at negative 150, right? So there are plenty of substances that it's not necessarily the heat side of it that makes the boiling point of water high. It's that you need that energy, that heat energy, to make the water melt, and boil, but also melt. So the strong hydrogen bonds on the surface of water make a coating which we call surface tension. So perhaps you've done the demo where you put, you have water and then something that's got a smaller neck, like a bottle. In class, I often use an Erlenmeyer flask because it's got that tapered neck, and the water, when it's closer together like that, will form a stronger surface tension. And you can actually, if you slide coins in without breaking really the surface tension at the top, you can actually get a dome at the top of the Erlenmeyer flask. The water doesn't spill out. I mean, there's a limit to this. Same thing here. This is a picture of a water bug. So it is using the properties of the surface tension and spreading out its legs. You can see how spread out they are, and it is, seemingly walking on water when really it's just exploiting the fact that water has a high surface tension. So another natural phenomenon is that ice will float when frozen. So again, the spaces between water molecules, because you get that strong matrix formed by the hydrogen bonds, then they're actually bigger, so it will float on top of the liquid phase. And this is important, right? You can imagine if when ice froze at the top of the lake, it sunk every single winter, then it would kill everything underneath it. Whereas when the ice freezes on the top, then it allows life to go on underneath. And it also sort of acts as a bit of an insulator as well. So you get the thick ice formed, and then even if the temperature sort of is crazy fluctuating above the surface, you've still got this ice layer that allows life to exist underneath. Certain life. And related to that is also what's called a high specific heat capacity, which if you took physics, you should have talked about. We'll talk about it in grade 12. So when you have a high specific heat capacity, it takes a lot of energy to lose, or it takes a lot of energy, or a body of water has to lose a lot of energy to change the temperature. So when those people who live near a lake, they often talk about lake effects, like lake effect snow. So let's say in Brantford, the concrete jungle, when there is that really super bitter cold, which means that it's often sunny, there's no precipitation, people say it's too cold to snow, right? Then if you live near a lake, what the body of water will do is make the air temperature a little bit more temperate. So the water absorbs all the cold, but it takes so much cold, such a decrease in temperature to make the water freeze, that the huge body of water will maintain its temperature for a long time. So in the winter, it takes a long time for the lake to freeze. It doesn't happen overnight, which means that you get what's called lake effect snow. So they generally have more snow days, for example, and then vice versa. If you've ever gone swimming and it's June and you think it's been 30 degrees for 3 days or whatever, and you think, oh, the air's so warm, and you go in the water and it's freezing, again, because it takes so long. Now the lake has spent all winter absorbing cold air and releasing the energy it had and changing its temperature, that it takes so long for it to warm up. And there are lakes up north that are much deeper than Lake Ontario and Lake Erie that will stay freezing for much, much longer. Okay. Oh, that's it. So I included a link to a Magic School Bus episode, and it's also on Netflix, season 2, episode 5, if you happen to have Netflix. It's called Wet All Over. It does deal with the water cycle, which you should have done in elementary school, but it also does, it talks about water treatment. So Brantford gets a bad rap about its water treatment, but it actually has what's called tertiary treatment, like not just primary, secondary. It's like the third level of treatment. It's actually got quite a few levels of water treatment. And so they try to go through what those levels are. So later on, you'll look at some data from the city of Brantford and look at what's in the water and what it means. Like, we'll talk about concentration and things like that. So it's a good intro, ease you into the next few topics. Okay, thank you. There are questions that are to go with this lesson that are on D2L. So it'll be all in the same submodule. Thank you.